Hello, and once again, welcome to the next session on organic spectroscopy problem. This problem I have borrowed from UCI, University of California, Irvine, and this question was posed by Professor James Novick for the PhD level examination, course examination in the last midterm test in November. And I thank Professor Novick, and let us straightway go to the problem, a beautiful problem. We will try to find out the structure, stereochemistry of the molecule for which the data, the spectroscopic data are given. First data is mass. The mass spectrum is not given, but the exact monoisotopic molar mass is given 132.0786, and we can find out the exact molecular formula. Since it is an even numbered molar mass, so the possibility of a nitrogen is ruled out usually, and we can refer to the table, the appendix of the textbook in the mass number 132, or we can use the chemcalc.org software. I'm just showing you the software. You can use the software chemcalc.org and come to the monoisotopic mass and put your exact precise molecular mass, monoisotopic mass 132.0786. The exact mass is matching with the first formula. The exact matching has happened. So the molecular formula is C6H12O3, and it cannot be N3. The number of nitrogen atoms is odd. So the molecular mass is even. So the formula has been found out to be, the molecular formula is found out to be C6H12O3. Then let us find out the unsaturation number, that is the double bond equivalent. Double bond equivalent is coming 6 minus 12 by 2 plus 1. It is 1. Only one double bond equivalent means there might be a double bond, carbon-carbon double bond or carbon-oxygen double bond. Let's look to, or it may be a cyclic compound. Let us look to the IR spectrum. IR spectrum conclusively tells us that there is a OH group, a broad but intense peak centering around 3421 centimeter inverse, speaks of the presence of a OH functional group. And there is no peak in the last part of the functional group region from 1800 to 1450, no peak, which indicates there is no carbonyl function in any form and no carbon-carbon double bond. That will definitely have peak at 1600 to 1400. At least one or two peaks would have come for double bond C and double bond O above 1700 usually. So no double bond is there, only OH, alcoholic OH function is there. The absence of carbon-carbon double bond is also confirmed due to the absence of any CH stretching above 3000. All are below 3000. So we don't get much information other than a OH function, right? Let us look to the proton NMR spectrum. This is the solvent chloroform peak. We ignore this and let us count the number of peaks. 1, 2, 3, 4, 5, 6, 7, 8. These two are singlets, and these is a broad singlet, possibly due to OH group, and these are multiplets, and the multiplicity pattern is not clearly observed. We have to expand the spectrum and see. Let us look to the integration value. The integral values are written below. all are one proton peak, 1 1 1 1 1 1, and these two peaks are 3 proton singlet. So this 3 3 indicates there are 2 methyl groups. Obviously there is no coupling because it is a part of dimethyl carbene group, so that there is no hydrogen here, no coupling, so each one is a singlet, and these two are non-equivalent. Might be there will be a chiral center which makes these two methyl groups non-equivalent, giving two closely situated, closely spaced methyl peaks. Now let us now look to the expansion of these peaks, and all are one proton peak, 1 1 1 1 1, and this is the OH peak. Obviously this broad peak, the OH peak, is always a variable position from 0.5 to 5.5 ppm depending on the extent of hydrogen bonding, and whether it is a broad peak or a sharp peak or a multiplet will be decided by the rate of exchange. So that is a very weird kind of pick which we can identify. So this definitely is due to the OH pick. There is only one OH, of course, and these are all CH picks. So there are 5 CH protons and 1 OH proton, altogether 6 proton picks, 1 proton picks, all are 1 1. So 6 1 proton and 3 3 6. So here the 12 hydrogen is now matched with the formula. There is no symmetrical structure, all the proton peaks are non-equivalent. So these only these methyl protons are methyl protons are also non-equivalent, so altogether 12 protons. Now these are the spectral lines, all the lines including the multiplet lines, the finer lines, all the lines, these are the data which we shall analyze very soon. Our interest is to see the expansion of these closely situated graphs, spectral patterns. Now let us start from 3.5 because these are already self-diagnosed. And starting from 3.5, we look to the expansion of the peak, we find it is a DD, doublet of doublets. So also the second one at 3.65. And the third one, 3.73, is also a DD. Fourth is also a DD. So there are 4 DDs. Each DD represents only one proton. We have already seen the integral peaks. All protons, all the multiplets represent one proton. And the last, the downfield peak at 4.2, about 4.2, appears to be a complex multiplet. We need further expansion to deeply see if the number of lines are very symmetrical, so that we can decipher it is not a complex pattern but it is a nearly first order spectrum, but maybe due to trespassing of lines it is looking like a complex pattern, but we can identify its true nature once we see the expansion. Let us look to the expansion. In the expansion we find there are 12 lines. This peak 4.19 is expanded to clearly distinguish between all the 12 lines. There are 12 lines. 12 line peak could be due to TQ, triplet of quartets, or QT, quartet of triplets, or DDT, doublet of doublets of triplets, or TDD, triplet of doublets, TDD. So you can try with any possibilities. You will be definitely be sure that this pattern is due to TDD, not DTT. And when the J values, because it involves 3 J values, in all the DDs 2 J values are involved, and the separation between the first and second line or the third and fourth line give you the small j, and between the first to third and second to fourth gives the bigger j. That is the rule we use to find out the 2 J values. But when there are three coupling constants, and when those coupling constants are close, then the inner lines often trespass. They are not separated so that you can see in a very clear and simple manner. You have to find out with a little trick. Now let us apply that trick. I have found out to be TDD, not DTT. See, the first is triplet. Theoretical triplet will be 1 is to 2 is to 1 triplet. Then each of the components of the triplet will be further split into a 1 is to 1 doublet. That means 1 is to 1, 2 is to 2, 1 is to 1. Then again each of the components will be further split into a finer doublet, 1 is to 1 doublet. So this TDD has 1 is to 1, for this 1 is to 1, 2 is to 2, 2 is to 2, 1 is to 1, 1 is to 1. So there are 12 lines, and you can justify in the similar way 1 is to 1, 1 is to 1, 2 is to 2. Here the two are 1 is to 1, and here is the trespassing has occurred 1 and its counterpart friend is here, because the separation are equal. All these separation 1, 1, 1, 1, 2, 2, all these separations are identical. You have to find out that. Is 1, 1. Then 2, 2. The first 2, 2. Then the second 2, 2 here. The second 2, 2 is here. Separations are same. 1, 1. Then 1, 1. In between the second 1, 1, the two, one of the 2's have trespassed. Then 2, 2. Then another 2, 2. Then in between these two, this one has trespassed. So 1, 1, then 1, 1. So because the coupling constants are close, so the pattern has been little weird looking, but if you look, it cannot be DDT. As many can say, could it be a DDT? No. If it is a DDT, then first will be 1 is to 2, 1 is to 1. Then 1 is to 1 is to 1 is to 1. Then 1 is to 2 is to 1, 1 is to 2 is to 1, 1 is to 2 is to 1, 1 is to 2 is to 1. So you cannot find, supposing you say 1 is to 2, a large separation between the first and second component, and 1 here. See the separation. And the next one 1 to 2, 1 is to 2 is to 1, the separation will be very, very small. This 1 to 2 is okay. But this 2 to 1 or 2 to 1 will be weird. Again, this 1 to 2 is to 1. So you can't get 4 1 is to 2 is to 1 here. But undoubtedly you will get 1 is to 1, 1 is to 1, 2 is to 2. Although trespassing has occurred, so undoubtedly it is a TDD. We will find out the 3J values very soon. Then let us look to the carbon-13 spectrum. Carbon-13 spectrum, ignoring the CDCl3 triplet 1 is to 1 is to 1 triplet, we find there are 6 carbon resonances, 1, 2, 3, 4, 5, 6. So there are 6 non-equivalent carbon atoms. 6 non-equivalent. And let's look to the depth experiments. Depth 135 shows there are 2 methylene protons, CH2. Because those lines which come below the baseline with a negative peak, those are for CH2 protons in depth 135. And those which are coming above the baseline, the positive lines, they are both for CH and CH3, methine and methyl. So to eliminate which one is methyl and which ones are methine, we have a depth 90 which will only give the methine. So there is one peak, so one methine proton, and so this one was methine, so that it is coming in depth 90, but these must be two methyl, so that they are not coming in the depth 90. So that we found one methine, two methyl, and two CH2. I'm so sorry. There are two lines, there are two CH2. But we already know from proton NMR there are 5 CH. How to account for the 5 CH? Undoubtedly one CH is there, but the 2 methylene group must be diastereotopic. So this is one methylene, this is the other methylene, and one CH. So there are 5 CH. Proton NMR will distinguish between these two, they are non-equivalent, diastereotopic. So also these two. But carbon 13 NMR with depth experiment, that will not distinguish between these protons. They will say that it is methine carbon, this is methylene carbon, and this is methyl carbon. So that will not. So carbon resonance depth experiment will tell two methylene, one methine, and two methyl, and we have already justified the presence of 5 non-equivalent protons, 5 CH protons, CH, 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 and 1 methine proton and 2 CH3. So what we have learned so far, let us try to build up from the part structures that we have collected from different spectra, try to build up the structure. We have known the proton NMR has 4 DDs, this now is known to be a TDD. We already know. It was appearing before we enter into the expansion. Now we know it is a TDD. So we know this, we know. Let us now try to find the J values. Before we go for structure, now first let us try to go for structure. Then we will find the J values in Excel software. Now my first guess, because I also solved this problem. When I found this problem, I tried myself to solve the problem without anybody's help. So I thought, since there is no double bond, no carbonyl function, it's only a hydroxy compound, how to justify DBE1 on saturation number 1? So it has to be a cyclic one. And there are 3 oxygen atoms, C6H12O3. One is OH from among them. What about the other 2 oxygen atoms? There cannot be anything other than a ring. So initially I thought, could it be a 6-membered ring, dioxane, 1,2 dioxane, so that you have one carbon containing the 2 non-equivalent methyl groups. Here is one chiral center with OH, and this is the chiral center that makes the 2 methylene protons diastereotopic, non-equivalent. So also these methylene protons. So everything is now set. I thought, so the depth experiment will say 2 CH2, 1 CH, and the proton NMR will give you 5 proton peaks, 1 proton. This is non-equivalent 1, 1, 1, 1, 1, and this has to be a DD. This is geminal coupling, vicinal coupling. This also DD. This is also a DD, vicinal coupling, geminal coupling. This will be a complex multiplet, or if the two J3 values are fortunately same on either side, this side or this side, then it will be a triplet first. If it is a larger coupling constant, triplet, and then the smaller 2 different J3 values on the other side will make it doublet and doublet. So triplet of doublets TDD. So I thought this could be the possible structure. Then immediately I had to be very suspicious. I tried to predict the proton peaks from the Sulleri rule table, from the data table from the book, Silverstein book. I found that these methylene protons can never ever exceed 2, less than 2 ppm, because on either side there are carbon atoms, not oxygen. But here it will exceed 3 because close to oxygen. Here this will exceed 3, and here this will exceed 3. So this was ruled out, only one ground, that these protons can never be above 2. And all the proton data are above, all the DDs are above 3. The starting value is 3.5. So this is ruled out. Then immediately I thought, could it be 1,3-dioxane? Then I tried to visualize the same thing, but just changing the oxygen position. This is OH and this is H, and as usual the 2 diastereotopic methylene protons. Same thing, DD, but there is a problem here. Then I saw, well, there is a plane of symmetry here, passing between this Structure has been weird, little bit weird. Please bear with me because I have to. So there is a plane of symmetry passing through this carbon and this carbon, which makes these two which are lying, supposing above the plane, equivalent, chemically shift equivalent, and these two which are lying below the plane also shift equivalent. And this is another, so there will be 3 proton peaks, one for the A group, the other one for the B group, and the third for the X group. The A group will be a doublet of doublet, DD. The B group is also will be a doublet of doublet, because there cannot be a coupling between A and A. Equivalent protons, they do not usually couple, and of course there's 4 bonds apart. And this one will be triplet of triplets, TT, 9 lines. We have 12 lines. Why TT? Because these two are same. Supposing this is higher coupling constant, so it will be first a triplet, this proton, and then each component will be a further triplets by the lower coupling constant. These two are same. So it would have been triplet of triplets, so 9 lines. We are getting 12 lines. So this is also ruled out. The number of DDs would be only 2. And TT, so altogether there will be 3 proton peaks, 1 proton peaks. It will be 2, 2, 1. In that case, 2, 2, 1. These two are equivalent, these two are equivalent, this is non-equivalent. So 2, 2, 1. And then OH, forget about OH and the methyl protons. These are, and moreover, these 2 methyl protons will now become interchangeable by sigma plane. So they will give you 6 proton singlet. So the number of proton peaks is reduced. 6 protons singlet, 2 protons DD, 2 protons DD, and 1 proton TT. That is we are not getting. These two are non-equivalent. So that is gone. Then I thought, is it 1, 4? Can it be 1, 4? Same thing. So if it is 1, 4, then there will be another problem. So this methylene will not be a part of this spin system. They are insulated by oxygen. So this will be a J2DD, each one will, sorry, doublet. Simply a doublet, this will be a doublet. Yes, it will be diastereotopic. There is a chiral center here. But it will not be a DD each, it will be a doublet each by J2 coupling only. And this would be a DD, this will be a DD, this will be a DD. So there will be 3 DDs and 2 doublets. But we are not getting, we are getting 4 DDs and 1 TDD. So therefore, I ruled out, of course, since there is a chiral center, you will be getting 2 non-equivalent, methyl groups. And so also there will be 6 non-equivalent carbons. These 2 carbons are also non-equivalent. So you are getting 6 carbon resonance, 1, 2, 3, 4, 5. These 2 are non-equivalent. Diastereotopic methyl groups. So the carbons are also non-equivalent. So you are getting 6 carbon peaks, not 5. In this case, you would have got 5 carbon peaks. We are getting 6. In all possibilities, this is completely ruled out. Now here, my final decision before I submit the answer was this. Then I thought, before submitting, I thought that this would be a DD. It cannot couple because this is a different spin system. So this is a DD. But you are getting 12 lines. How could you account for 12 lines? And what about DD? This is only a doublet. There is no coupling with any other proton. There is J2 coupling. Therefore, this was ruled out. Finally, my attention went into 5-membered ring. So I then thought it could be a 5-membered ring dioxo compound. Then I first thought, could it be 1,2-dioxolane? This is dioxane, this is dioxolane. So that on one point dimethyl group and the other point will be H and OH, and this will be HH. So in that case, you do not find, although the formula will be satisfied, one will be CH2OH, I'm sorry. The other carbon will remain in the form of CH2OH. I'm so sorry. So let us now think of a 5-membered ring where the 2 oxo group are in 1,2 position. Other one is this. The third one is CH2. These are the 2 non-equivalent protons, and this is OH. And these are 2. So when I take this, then I could not find this one. This one is okay. Uh, this is a DD, this is a DD, this is a DD, this is a DD. Okay, fine. But what about this? The multiplicity of this CH peak would be on one side, okay, DD, 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 CH3 will be there is no there is a chiral center here. Then this could be a possibility where the 1,2-dioxolane could be a possibility where you can justify the peak positions. But if you look to the data, I mean Sulleri rule data, you will not find this going below, I mean above 4. It will not, it will be 3, it will be less than 3 because the OH is 3 bond apart, 1, 2, 3. So this methine proton will be less than 2. If it is directly bonded to O, there is no hydrogen here, O, there is no O here, no O here, no O here. So this methane proton can never ever go above 2. So we are not getting any peak below 3. All are 3.5 and above. So this possibility is ruled out. So the only possibility left is 1, 3. So 1, 3, that gives the best solution, and 1, 3, this is a dimethyl, and this is the chiral center, and this is close to oxygen, therefore it can exceed 3, and not only 3, it has exceeded 4. Why? Why? Because it is 2, 1, 2, 3 bond apart the second oxygen, and also 3 bond apart the third oxygen. So this is, and moreover it is methine. Methine is less than methyl and methylene, so that if you go for the Sulleri rules table prediction, you will find this is the most downfield, followed by this, followed by this. So I assign this methine peak to 1.49, and that is TDD, and this methylene CH2OH to be 3.99 and 3.73, which are close to each other. I gave you the data, 3.99, 3.73, these two DDs are given to the methylene close to hydroxyl group, and the other ring methylene is given 3.66 and 3.55. All are DDs. How they are DDs? Now this is geminal coupling, one doublet, and this is vicinal coupling, the other doublet. So each one is a DD, this DD, this DD, this DD, the vicinal coupling and geminal coupling. But by calculating the J value, we find that this one having 3.99 and 3.73, they couple equally to this proton. The J3 value is same 6.5, 6.5, and so also J2 has to be same for this and this because they are bonded to the same carbon. But usually the J3 values, trans and cis J3 values might be different, but here we find the same values. But the other one, we find two different J3 values. But J2 value is larger than this. This is 8.2, this is 11.6. But one of them J3 couples with 5.3, the other one J3 couples with 3.9. I shall show you the calculation very soon, right? Since these J3 values are same on this side and it is bigger 6.5, these J3 values are smaller 5.3, 3.9. Therefore, this proton first couples into a theoretical triplet with the same coupling constant 6.5, and each of the component is further divided into doublets 3.66, and again each of the components further divided into final doublets 3.5, 3.9, I'm sorry, 5.3 then 3.9. First 6.5, then 5.3, then 3.9. So it will be triplet of doublets TDD. Now these are the two non-equivalent methyl protons, 1.32 and 1.39. Those are singlets. This is a TDD, this is a DD, and this has same J3 6.5, 6.5 and J2 8.24, and these have different J3s 5.3, 3.9, but J2 has to be same. But this can have two different possibilities. The stereochemistry might be opposite. This is one enantiomer where hydrogen is below the plane. This is supposing R, and hydrogen can remain above the plane, which is S. So we cannot assign whether this is R or S, because only from formula and data, unless there is a 2D NMR nosy data, we cannot assign the configuration. We cannot say whether this is 3.99 or this is 3.99 or this is 3.73. We can interchange. We can interchange between them. We can interchange between them. We cannot say with 1D NMR data and other supporting data without 2D NMR, we can't assign which diastereotopic protons and methyl groups the ppm values can be assigned. Cannot do that, right? But we can now say that R and S equally suitable for the data, but no other structure can fit into these data. But let me tell you how you can find out the J values. First, I ignored the 12 lines. I did it last. First, I tried to analyze the DDs. The first DD, the CS2, one of them is 3.99. The first, second separation and third, fourth separation will be the small j, 6.58, 6.57, and I made a average of these two, the j small, and then the j big will be 1/3 and 2/4. First and third, second and fourth. That separation is the big J, 8.24, 8.241, and I averaged it to 8.24. So I got the DD J values 8.24 and 6.5 as the two J values for the first DD. The second DD of the same diastereotopic methylene protons I got in the same manner 8.24 and same 6.5. So these two might be different in many cases, but here I found the same. But the other methylene belonging to the ring, 5-membered ring, I got a different J3 values. So this is 3.66. The same manner I got the smaller J to be 3.9, and the bigger J 1.3 and 2.4 I got 11.6. So averaging we get 11.6 and 3.9. And its partner, the other diastereotopic proton, I got the J value not 3.9 but 5.3 and 5.3. So 5.3, and the J2 value has to be same, 11.6, 11.6. So this is 11.5.3 and this is 11.6, 3.9. So the J3 values are different. So all these fit into, because that is why then I thought of, then this is OH 2.5 broad singlet, and this is a methyl proton singlet and singlet, so there is no question of J value. So then I came into analyzing the 12 line data, 1:1, 1:1, 2:2, 2:2, 1:1, 1:1. So these are the intensity lines. So you can fit 1:1, 1:1, then in between 2:2. The slight departure is obvious because in any such spectra, even we call fast order, but some non-fast order tenting effect will be always there, we have to ignore. So not that it is exactly 2 times. So 2 times of this is 5525370. So this is 1 is to 1, 1 is to 1, 2 is to 2, 2 is to 2, 1 is to 1, and then 1 is to 1. 1 is to 1, 2 is to 2, 1 is to 1, right? So they have trespassed. 1 is to 1, 1 is to 1, 2 is to 2, 2 is to 2, 1 is to 1, 1 is to 1. So the best method that I have learned from Professor Hans, who unfortunately is no more, University of Wisconsin, is by reduction method to find the J value from the lowermost to the uppermost. So the small J value in such kind of trespassing multiplets of multiplets of multiplets, that case what I find, the first line, second line, last line and last but one line will give you the lowest J, smallest J, always, no trespassing. So then I average this value and then reduced this TDD to TD, triplet of doublets, triplet of doublets. So I average these two, I average these two, I average these two, average these two, these two, these two. So I put this value, average values here. I get 6 lines. This is the reduction. 1 TDD, from the TDD, the last D is out. Then we are having TD. So then TD, we have to go for the first 2 lines, then these 2 lines, then these 2 lines. 1 is to 1, 2 is to 2, 1 is to 1, right? 1 is to 1, 2 is to 2, 1 is to 1. So the separation I found out here, this is a small j value, which is the separation is about 6, yes, this two separation is this 5.3, this is the intermediate j value, and the big j value will be 1, 3, 2, 4, and 3, 5. So, or it is better by reduction method. You take the average of these two, take the average of these two. I have taken the average, these two average here, these two average here, these two average here. Then it is reduced to a triplet alone. So when you reduce the TD, it will become a triplet. The mid position of this, mid position of this, mid position of this. Then the separation between these two will give you the big J. Big J, there are two big J values and I average to 6.55. So the TDD has a biggest J value is 6.5 and the intermediate 5.3 and the smallest 3.9. 3.9 is the difference between these two, these two, these two, these two, these two, these two. So you can identify from the separations, right? So is it not interesting how to play with the data, the NMR lines data, the spectral data, to separate them? You know, there was no separation. I separated because once you find a big jump, you know, J values are comparable. It is less than 20 hertz. It cannot go beyond 20 hertz, subsequent J values, even 1 to 3, 1 to 4. But when you find a large jump, 80 hertz, 70 hertz, 50 hertz, 100 hertz, then you are entering into another peak, not the same peak. So I found the difference are small, 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 small. Suddenly there is a big jump of about 100 hertz. So definitely we are entering into another peak. So I put a line, so I counted there are 12 lines, it could be TDD or DTT or TQ or QT. So I analyzed separately the expansion, it told me it is a TDD. 1 is to 1, 1 is to 1, 2 is to 2, 2 is to 2, 1 is to 1, 1 is to 1. Everything is there, but trespassing has occurred. You have to be very careful. And the other one, I find the jump after 4. So this is a DD. Other one, I found a jump after another 4. This is a DD. Then another DD. Then another DD. So I demarcated all the different peaks by looking to the big jumps. Then this is a OH peak at 2.45. These are again different positions for the two methyl groups, methyl. So I have to identify, I am to demarcate the lines which belong to which peak. Then I count the number of lines, the DD, then analyze the complex, so-called complex multiplet, which is a mere TDD, and then I found the J values using Excel, and I already have completed the structure to be, you know, 1 2-hydroxymethyl 5,5-dimethyl 1,3-dioxolane. Could be R, it could be S. We cannot say from these data whether it is R or S, we can't say. And the carbon resonances are also assigned just at par with respective to the shielding desilting effect of the protons. I assigned the quaternary carbon to be 109.4, this quaternary carbon flanked between two oxygen atom, and this quaternary carbon flanked by only one oxygen is 77.2. And since this ppm proton ppm was more 3.99 3.77, so I assigned 65.7 to this carbon, 63 to this carbon, and the two non-equivalent methyl carbons are given 25 27. But these assignments are really tentative. We can only confirm if we have 2D NMR data, particularly head core data, HMQC or HSQC. Then we can say which carbon is bonded to which two hydrogen atoms or which one hydrogen atom. We can say that. And anyway, whatever data are given to the students in UCI, they will definitely, and interestingly, it is a compound which is an acetal produced between acetone and glycerol. CH2OH, CHOH and CH2OH, the two vicinal hydroxy groups, they reacted with the acetone forming this acetal 5-membered ring, and one CH2OH is left out. So this is an acetal produced from the reaction of glycerol with acetone. This is a very simple compound that the students synthesize in the laboratory, acetals, that which Professor Novick very intelligently chose this compound. I think we close today's session. And how did you like this session? The analysis of a problem that was set in a PhD level examination, the qualifying for PhD course that was set in UCI, and you compare in your university how you face the question for PhD level or elsewhere in the graduate level, and come in touch with me. Any doubt you have, you can directly contact me. I am SS Tripathi. My channel is SST Chemistry, you can find, and I will be having continuous spectroscopy problem series, and also the theory sessions also will start very soon. So my passion has been to work on to study and teach on organic spectroscopy, and now I am starting videos. Like and subscribe if you have not. Bye bye.